Okay, today we're going to review, by the way, I don't see Austin, I got everybody else here. We're going to review, but I do want to get one thing in for the homework on Wednesday before I get into the review. In the class on Friday, I talked about the disintegration energy. That was the E disintegration was the mass of the parent minus the mass of the daughter times c squared. It comes just from Einstein's equation relating mass to energy. And it turns out when you have a radioactive decay, you go to a lower mass in the daughter products than you started with the parent product. And thus, you have a difference in energy of the materials. The difference is released as a photon or something else. Well, you have homework problems that ask you for the binding energy. The binding energy is the same equation, except for it's going to be the mass of the constituents minus the mass of the atom times c squared. So what are the constituents? Let's just do a real quick example of the binding energy. Let us take, I don't have any numbers at hand, unfortunately. Let's take, somebody have a textbook or something like that so we can look up the mass of a nucleus? Yeah, Google, okay. Works for me. Let's take iron. Iron is what? Yeah, I was right. It's 26. And what's the most common isotope of iron? When you look there at the
56 or 57. Doesn't matter.
Yeah. Look up 56. Yeah, that's what I was thinking. So iron 56. The mass of iron 56 is equal to
You'd think it would have.
that bottom number is the one we're going to calculate. Working. Since Chad's not finding it quickly, somebody with the textbook just want to, or yeah, you've got the computer open, look in the table. The mass of an atom of iron 56. No, this is for the homework on Wednesday. Yeah, it's from chapter 31, but the numbers are in the first appendix after. What?
Just the mass of iron 56 in general?
Yeah.
I found 55.9349375.
55.9 what?
9349375. Assuming we trust Wikipedia.
Why not? So there's our mass of the atom. Now, what are the constituents of the atom? Constituents are the things that it's made up of, the things that constitute it. So it has, let's start with neutrons. How many neutrons? 30. How did she get 30, everyone? Yep, just subtracted A minus Z. 56 minus 26 is 30 neutrons. And what's the mass of a neutron? See plenty of computers open somewhere.
675 times 10 to the negative 24.
In AMU. 8664 or 9 what?
91588. That's the 10, yeah.
Okay.
That's right, but again, let's figure it.
And then we have protons. How many protons?
26.
26. How does she get protons as 26? It's the bottom part. And what's the mass of a proton?
$1.007.
1.007.
2766.
2766.
This is from another.
Do you disagree? No, okay. And then electrons. How many electrons?
There should be 26 if it's neutral.
Okay, there should be 26 if it's neutral. When we list the mass of an isotope, we show the mass of a neutral isotope. So it should have the same number of electrons. What's the mass of an electron? 0.005 what?
54858.
And I do have the right number of zeros, correct? 2 zeros after the decimal?
3 zeros after the decimal.
Because obviously that would have made a difference. Okay, so I have the constituents listed and I have their masses. Obviously, if you're binding energy problems, I think I've assigned 2. You're going to use the same constituent masses, but you'll have different numbers. So now to find the binding energy, so I have the mass of the constituent, so I'm going to have 30 times the mass of a neutron plus 26 times the mass of a proton plus mass of an electron times c squared. Whoops, I forget. I need to do minus the mass of the nucleus, so minus the mass of iron 56, then times c squared. So then I just put in my values. That last number is the conversion factor to convert from atomic mass units into MeV per c squared. So 931.494 MeV per c squared U, and then times c squared. So as you do the calculation, notice the c squareds here cancel, and then the u's cancel throughout. And I'm going to be left with MEVs. And I am trusting Tori here is doing the math for me.
I got 492.26.
492 point what?
2616566.
Okay, now in terms of significant digits, we have to look at what we had. We were good to the 1, 2, 3, 4, 5, 6, 7, 8th digit there. 1, 2, 3, 4, 5, 6, 7th digit there. So we were good to total of 8 significant to the 8th digit. No, 7th digit, and things we're adding. And so we basically are going to be, I think, 10 significant digits in our answer if that was it. So my limit is going to be my conversion factor. 3 significant digits in my conversion factor. Probably should have gotten a better conversion factor since we had better significant digits. So, yeah.
And then for the homework, it wants us to divide that by the number of...
Right.
Okay.
you usually find the binding energy per nucleon. Now, yeah.
Question. How did you get from the 931 to, was that you just converting it?
Okay. The 931.494 is a constant you can look up. That's a conversion factor between mass units. And so this whole calculation, I have this equation. I substituted in for just this part. That's this line. So that's all the substitutions. Then I inserted my conversion factor, which has the square around it, except for the units. And then I have the final c squared is right there. So I just substitute numbers into the equation that's in the big box. Okay, so we have this binding energy, and we usually want to know the binding energy per nucleon. How many nucleons are in iron 56? 56. So we just take that number, 492.2616566 MeV, divide it by 56 nucleons. And what do we get?
8.7903866726.
Okay, I'm going to stop at 3 at this point. So we get 8.79 MeV per nucleon. Assuming we did our calculation right, I think that's probably correct. Iron is the most stable nucleus. And so if we have fission reactions, bigger things breaking up, well, things breaking up, they have to break up into things that are closer to iron, which means they have to be bigger than iron if they're going to break up into things that are closer to iron. If we have fusion combining nuclei, they have to combine to form something that's closer to iron, so they have to be smaller than iron for fusion to occur. Hence, in stars, a normal star like our sun is fusing hydrogen to helium in its core. When it runs low on hydrogen, the reaction rate will slow down, it'll start being compressed, and it'll start fusing helium into carbon. When it runs out of helium, which will be like only 10% of the time it takes to run out of hydrogen, it will shrink some more, and it won't reach a high enough temperature and pressure to fuse carbon, so that'll be the end of it. Larger stars will start fusing carbon, oxygen. They will end up producing an iron core. But when they get to the iron core and they're out of the constituents that made the iron core, they start to contract, and there's no more fusion that's going to release energy. That's the end. That's when you have either the formation of a neutron star or a black hole. You have the supernova. Okay, so I wanted to make sure I covered that because you have homework that has that on it. It's still just the same techniques of the problem that I worked out in class on Friday, but we had to have the actual constituents rather than this atom and this atom, what we had for the daughter products when we did it before. Okay, the exam tomorrow will be like all the other exams. I'll try to have about 50% conceptual and 50% problems you work out. Because students wanted more exams, which to me seemed weird, this is the first year that I've had 4 exams during the semester, so there wasn't an exam 4 from previous years to compare. So I just took problems from the practice problems and worked them out and posted those so you have some solutions you can see for the worked out problems from the practice problems. I didn't do any conceptual ones on that. Actually one was conceptual, the one that this is not possible. So you can look on Moodle, and there is some practice problems for exam 4. Just they're solved problems from the practice problems at the bottom. Okay, let's quickly is a relative term, look over the material that we're covering on this exam. I did not mean to be funny. I'm just a funny man. Yeah, I wish. Okay. One of the first things about relativity is make sure you understand what an inertial reference frame is and why it's important. So just because it's important, what is an inertial reference frame? Okay. A non-accelerating reference frame, what makes it inertial? What does the word inertial actually refer to?
Obeys the law of inertia.
It obeys the law of inertia. It obeys Newton's first law. That is, an object will stay in constant motion unless There's a force acting on it to change its motion. We're used to inertial reference frames. But if you are on a merry-go-round and you consider yourself stationary on this merry-go-round, you don't look at the world around you, just look down, that's a non-inertial reference frame. Because if you had a marble sitting down at your feet, it wouldn't just stay there. It'd go flying off all on its own, right? And it's easy for us to say, well, sure, that's because you're rotating. But the fact that you're rotating means you're accelerating. That's what makes it non-inertial. Why is this important? Because special relativity is only dealing with calculations made in an inertial reference frame. So if you have a non-inertial reference frame, an accelerating reference frame, you can't use what we've learned about relativity. Now, I had students send me email about differences in special relativity and general relativity. One of the big differences is we haven't talked about general relativity. Everything we've talked about is special relativity. Special relativity is the simple part of relativity. General relativity is the hard stuff. So we didn't do that. General relativity is the fact that a large mass will warp the space-time continuum. That means that light bends around massive objects because the space-time continuum is warped, so a straight line to us looks bent. Likewise, time travels at a different rate, which is why the GPS system, the clocks, don't keep correct time when they're on Earth, but when they put them out in orbit, then they keep correct time. So that's what the general is. Make sure you understand what relativity is fundamentally about. It's about comparing the measurements made in one reference frame to another reference frame. That's where the term relativity comes from. This measurement relative to that measurement.
So which one deals with the inertial frame? General?
The special. Special. And so we had Galilean relativity. Oh, I almost forgot. This is a sheet to indicate your transportation desires for Friday. I will give you on Wednesday more information about the field trip. The best time to go is in the morning, like from 8 to 10, and then you'd be done. I will actually be driving out there around 8, coming back to teach class at 9:30, then going back afterward. If you want to stick around, I'm chair of a session that's a history of science that has exactly one talk, like at 3:30. So on this, indicate the first column here is if you plan on having Union College, van means Union College, supply your transportation, or if you're going to find your own, either your car or a friend's car. And then the next columns after that are if you're going to use Union College transportation, when would you want to use it? So write fill out your line and pass it on. You had a question, Cassie?
What were the requirements there? Was it to attend 4 sessions?
You have to attend 4 sessions and keep notes on them.
Okay.
And 2 of them have to be on a list that I will specify.
Will you give us that list?
I will give it to you in class on Wednesday.
Are those in the morning then?
I will have times throughout the day to try to accommodate different schedules. Yeah.
Do you know when that last or that big lecture is?
The Mayburn, something like that. It's, I think, 11 to 11:50 or something. The time here for the van returning that's scratched out and has the number changed, that means you're staying through the Mayburn lecture and then you're leaving. Do you not have something to write with?
Well, that's not the issue. I just don't know at this point.
And if your name is not on there, we need to know. That means somehow your form didn't get processed. Okay, back to the lecture. Make sure you know the postulates of special relativity. The first one, that the laws of physics are the same in all inertial reference frames. So you don't have to learn a new physics if you are on a spacecraft compared to being on Earth. The second one is the speed of light in vacuum is a constant in all reference frames. That came from experimental results. And with those 2 postulates, Einstein was able to show we have a big problem. And the answer to that was the idea that the space-time continuum can be warped, that spaces are not the same in different reference frames, that times don't pass at the same rate in different reference frames. Simultaneity. Remember I talked about my cousin Rob shooting the gun and hearing the sound, seeing the light? That is actually not a relativistic example of this statement that simultaneity depends on reference frame. Because I could have used my standard Earth-based physics and calculated the time for the sound, calculated the time for the light, and found that I found the light and the time, or the light and the sound at different times because they occurred at the same moment but had different speeds. So that's not the actual key for simultaneity. Simultaneity is that in different reference frames, things are actually, this was simultaneous in one reference frame, it's not simultaneous in another. And so it's something that we have to be aware of. It seems really bizarre. It seems impossible because we're always in one reference frame.
So, okay, something about if something is traveling at a faster speed than the particles and all those things around them are slowing down in their processes as well because it's going closer to the speed of light?
Okay, you have an observer.
Okay.
And that observer is always going to measure things in that observer's reference frame that are stationary with their proper time, which is always the shortest time possible. So the time for the heart between one heartbeat and next. Your measurement is always going to be the shortest time possible between that. Another observer who's moving relative to you is going to measure a longer time between the heartbeats. Not because they're farther away, because they're moving at a different speed than you. It's not a distance issue. It's a speed issue.
So when they're measuring each other's hearts, how are they moving? Or what's the...
Well, we have to do contrived things like you have a little light that flashes each time your heart beats or something. But right, we're not really measuring heartbeats when we're doing relativity. But it's a nice example of how calculations work. Okay, remember Einstein's clock? That clock that had a little light, a mirror, and a detector. As you have light goes from the light to the mirror back to the detector. Make sure you understand how that clock works in theory and how the outcome of that clock then gives us our equation for time dilation. Right? That clock gave us our relationship that said the dilated time is equal to gamma times the proper time. Proper time is always the shortest possible time between two events. And then using the proper time relationship and something traveling, we find that the distances are going to be different for reference frames. And so with the distances different, we have the idea of proper length, which is the proper length is the longest length that can be measured. And the relationship between length and proper length is that. Now, of course, I give you the equations. You don't have to memorize them. But you do have length contraction because gamma being defined as 1 divided by the square root of 1 minus v over c squared. That was a very poor place to put that. Somewhat better place. Gamma is always greater than or equal to 1. So that means delta t is always greater than or equal to delta t 0. The dilated time is always greater than or equal to the proper time. That's why we call it dilated. It grew. The contracted time, L, is always less than the proper time, L0. Hence the term contracted. You need to be able to identify the reference frame that is the proper length versus the reference frame that is the proper time. Right? Because if you can't identify which reference frame is which, then you're going to be throwing darts. You have at best a 50-50 chance of getting the problem right. Instead of a 100% chance if you, well, not 100%, but, you know.
Can we go through that again really quickly?
Yes. The proper time is the time measured in the reference frame where the object is stationary. So the starting and stopping points are the same place and they never moved. The proper length is the length measured in the reference frame where the starting and ending points are not moving. So in the simple example of a rocket traveling from Earth to Proxima Centauri, the distance from Earth to Proxima Centauri is going to be a proper length in the Earth's reference frame, because as far as the Earth is concerned, Proxima Centauri is stationary and so is the Earth. Now that's a rough estimate because Proxima Centauri is not stationary. But the rocket sees Proxima Centauri hurtling toward it, and it sees the Earth flying away from it in the rear. So it sees the starting and ending points moving. And so for that trip, the rocket measures a contracted length, a shorter length, and the Earth measures the proper length, the longest possible length. For the time for the trip, the person in the spacecraft sees his clock as stationary the entire time, and his clock is at the start of the trip and at the end of the trip. Hence, the person in the spacecraft measures the proper time for the trip, and the person on Earth is going to measure a dilated time. So the person on the spacecraft measures the shortest time for the trip, the person on Earth measures it took longer. Hence, the person on Earth is going to be older than the person in the rocket when the rocket returns.
And we're just explaining the twin paradox.
Which is the twin paradox.
Okay, I was going to say we're just doing that in terms of, because you said that the actual is in something to do with acceleration. But
Right. When you have two people passing each other, two ships in the night, you're going to have each person says, you're aging more slowly than I am. And they're both right, which is part of the bizarreness of relativity. But for them to come back together, one of them had to accelerate. And during the acceleration, then you have a very different thing measured by the one that's accelerating. And so only the one that stayed in the inertial reference frame is going to be correct for when they come back. So that's what removes the paradox from the twin paradox. The one who was inertial throughout is going to have the correct calculation. The one that was accelerating during the times of acceleration, they can't apply special relativity. And they would have something very different for that part. And yes, most of my review slides are on special relativity. The final one on special relativity, I believe, is know the difference between the classical and relativistic velocity addition. Remember, we had, for classical, velocity of AC is equal to velocity of A with respect to B plus velocity of B with respect to C. But for relativistic, we had velocity AC is equal to velocity AB plus velocity BC over 1 plus velocity AB, velocity BC over C squared. In both cases, the inner two indices were the same, and the outer two indices were the indices of what I was looking for. And what these means is velocity of A with respect to C, velocity of A with respect to B, velocity of B with respect to C. So make sure you can use those. Now this one here is for parallel velocities. For perpendicular velocities, we only did that in the calculus-based class. So only those people are going to be tasked with having to know that. What was that? Parallel velocities, yeah. Now the second part is be able to work with the relativistic forms of momentum and Newton's second law. Remember, one of these two equations is incorrect. That's correct. Why?
It's a simple version.
Yeah, because it's a simple version. The first one does not account for things like the distances and times being contracting. In the second one, remember, momentum relativistically is equal to gamma mv. So the momentum with the relativistic term has to be put into that equation, but it's still a correct equation. One of the things that you see from this is, if I want something to reach the speed of light, the faster it goes, the bigger gamma is, and the bigger the force is going to be needed to give it an acceleration, to give it a change in momentum. And so you get to the point as the speed approaches the speed of light, gamma approaches infinity, you would have to have an infinite force to change the momentum at that point. Hence, you're not going to speed it up anymore. Okay, so we have the relativistic equation for momentum, and then we have the three forms of energy. Rest energy. Famous equation, except for everybody forgets to put that little subscript 0. What is the rest energy? It's only 0 for a photon. Everything else has a rest energy greater than 0. What is the rest energy? Okay, energy stored as mass. It's the energy something has just because of its existence, because it has mass. Then we have the kinetic energy. Gamma minus 1 mc squared. Very different from our normal equation in that we don't explicitly see the speed of the object in the kinetic energy equation. It's there. Where's the speed of the object in the kinetic energy equation? It's in the gamma. And in fact, at low speeds, gamma is approximately equal to 1 plus 1/2 v squared over c squared. If you plug that in, you find that at low speeds, kinetic energy is 1/2 mv squared according to the relativistic equation. So the relativistic equation gives the same answer as classical physics if you're at a classical speed. But if you're at a relativistic speed, what makes something a relativistic speed? Okay, somewhere around 10 or 1%, 1 to 10%. 10% is probably good. 10% or greater the speed of light in vacuum. And finally, we have the total energy. Gamma mc squared. And so we have an energy balance. The total energy is equal to the kinetic energy plus the rest energy. So gamma mc squared is equal to and of course that's true. Minus mc squared plus mc squared, yeah, those add out to 0, and we have gamma mc squared equals gamma mc squared. But we have that energy balance. So those energy equations you also need to be able to work with. Now that's my conclusion on relativity. Any questions on relativity before I move on? All right, I saw 2 people shaking their head. No, I got this. Now quantum physics. It's important that you actually can identify what it means for something to be quantized. So you can tell the difference in quantized versus non-quantized variables. Simple example. Cell phones are quantized. Here's 1. Here's 2. They're not using them or anything. I'm not bashing on them here, just using them as examples. But you can't have 1.6359 cell phones. They're in only specific values. That's what quantized means. And our first introduction to quantized things could go all the way back to things, counting numbers when you were in elementary school, right? Those are quantized. 1 alligator, 2 alligator, 3 alligator. I was practicing my quantum physics back then. Yeah.
So what if you have a broken cell phone and you have like half of it? Is there like a way that to specify it has to have this and this and this in part?
Well, at this point, I would say it's not a cell phone; it's something else.
Okay, so it has to have a certain amount of parts that make it a cell phone, or
you're trying to go too deep into my simple example there. If you want something that you can't break, you can talk about, for instance, the charge charge comes in units of 1/3 the charge of an electron in quarks. There is nothing you can do to get charge in anything that's not a multiple of 1/3 charge of an electron. And in fact, since quarks don't come naked, it turns out in reality you can't get a charge that is different from an integer multiple of the charge of an electron. But because you can say, well, you can subdivide, that's why I use the 1/3. Since you're saying, what if I break an atom? If I break a proton? You can't, but if you did, you'd have that. So you need to know what quantized means, and then black body radiation. Know what was going on with black body radiation, what the predictions from classical physics as worked out by Rayleigh and Jeans, whatever. Know what classical physics came up with for their predictions for black body radiation. If you're confused, you can ask Charday and her group because they've got it on their poster. Right? Right. Okay. And Planck found an equation that actually fit the shape of the black body radiation, but he didn't have a reason for it, so he sat down and got to work, found a reason for it, but that reason required him to make a quantum hypothesis, a hypothesis that the energy came in only quantized levels. And then Albert Einstein said he was right, that light has to come in only integer multiples of energy that he called photons, the particles of energy. This was a big break for physics because prior to Thomas Young, we had the world of Newton that said that light was a particle, the corpuscular theory of light. But Thomas Young's double slit experiment that was on the last test showed that light had to behave as a wave. And now Einstein is saying, no, light has to behave as a particle. This is a big, big shift in physics. Right? It's what knocked physics on its head and gave us our modern physics era. And so Einstein proposed doing the photoelectric effect experiment, and you have the predictions of wave theory and the predictions of particle theory. And the predictions of particle theory are the ones that you found when you did when you did the experiment, are what is held up by the photoelectric effect. So this is an experiment that said light is a particle, not a wave. And you might remember that clicker question I had where I termed things differently. I didn't say it disproved the wave theory because scientists had two experiments that were diametrically opposed. One that would disprove particle theory. That's what Thomas Young's experiment initially was used for. One that disproved the wave theory. And so scientists decided that they must be complementary. That the true nature of matter must be complementary, must have both the particle nature and the wave nature. And of course, that brought us to Louis de Broglie, who's on, I think, the next slide, who said, if light has a dual nature, then shouldn't other things? What would make light so special? Now, light is special. It's special because it's the only particle with no mass. But de Broglie said, shouldn't other particles have the same dual nature? And quantum physics is based on, yes, other particles also have that dual nature. I did say here, I think, the energy electromagnetic spectrum is reviewed, and pay special attention to the energy needed to ionize things, right? Because when we have things like sunlight, we don't care about sunlight so much except for if it's in the ultraviolet range where it can start ionizing things. When we talk about radiation, we care about the radiation mostly when it can ionize things. So my cell phone, it can't ionize anything, and thus I don't worry about it here in my pocket. Although it is putting out microwaves, and we do heat up our food with microwaves. So it could be heating me up. But it shouldn't be ionizing, it shouldn't be breaking any bonds. X-rays. Remember the X-ray tube? You shoot electrons into your target, and out come photons. It's exactly the opposite of the photoelectric effect. The photoelectric effect, you shot in photons, and out came electrons. So the X-rays are just the reverse of the photoelectric effect. Make sure you understand what makes both the smooth portion of the X-ray spectrum. I am going to write to the book people and ask them why they have an incorrect figure for that. as well as the characteristic lines. So very shortly, since I said make sure you know them, what causes the smooth part of the X-ray spectrum? Slowing of electrons. They're slowing down. It's just German for breaking radiation, or so I'm told, because I don't know breaking or radiation in German. But the Bremsstrahlung is that breaking radiation, the radiation from it slowing down. What causes the peaks? Okay, it's electrons falling down to n equals 1 or n equals 2 from higher states. And so we actually use the spectroscopic notation that we learned in the next chapter, in chapter 30, to just define those as things like K alpha, K beta. The K is telling us the shell. That's the n number. If it's L alpha, then L means it's n equals 2. K is n equals 1. Okay, I already talked about de Broglie and why he came up with that, part of his 20-odd page PhD thesis. Then we have Compton scattering. Compton scattering was, again, something that shouldn't happen because you had particles that changed their wavelength without changing the speed. If they changed their wavelength without changing the speed, that means they changed their frequency. But that one of our rules for waves was they can't change frequency. And so that violated wave theory. What was the answer? Particles of light, photons, are bouncing off of electrons just like a BB bouncing off of a bowling ball. And when the BB bounces off of the bowling ball, you're going to have a change in the kinetic energy of the BB, a change in its momentum. And correspondingly, you're going to have a change in the kinetic energy of the bowling ball and a change in its momentum. And using conservation of energy and conservation of momentum, you can solve for what they're going to be based on angle. And so Compton did those calculations, but had to use the energy of a photon and the momentum of a photon to do his calculations. And those calculations perfectly fit the experiment. So he did the experiment first, he found this crazy, bizarre behavior, and then he went back and using particle physics was able to explain it. Heisenberg uncertainty. Werner Heisenberg's uncertainty is not a limitation on our ability to measure things. I mean, I, like most students, thought, well, if I measure the position super accurately now and super accurately later, then I could know the momentum in between super accurately, and I would know both. But the problem is, the momentum is changed each time you make a measurement. And so I knew the position really accurately, but I changed the momentum. Knew the position really accurately, but I changed the momentum again. I didn't know the position and momentum at the same time. And that's the basis of the uncertainty principle. You might remember I went through the wave packets to describe how it physically works. That is a mathematical relationship. The equations basically say we cannot know. Finally, atomic physics. Make sure you know what the different models of the, quote, modern atom are, starting with the plum pudding. So, plum pudding. Why was what necessitated coming up with the plum pudding model? The cathode ray tube experiments. Cathode ray tube experiments, that is essentially making a TV tube. It showed that you had electrons in matter. And so after you determined that you had electrons in matter, they said, well, that means matter must have positive charge all spread out, but you have just these little points of negative charge. So it answered the measurement of, there's electrons in here, there's little points of negative charge. But then the experiment done in Rutherford's lab showed that atoms were mostly empty space, but they had a really dense portion. And so mostly empty space with a dense portion required a change, right? That doesn't fit with the plum pudding. And so Rutherford came up with his planetary model that said that the electrons are doing circular orbits around the nucleus. And that explained the mostly empty space. But it failed miserably in that it suggested that electrons should only orbit for like a billionth of a second, and then they crash into the nucleus. And electrons should have any old energy rather than the very specific emission and absorption lines that we observed when I brought in the little gas emission tube. And so within a couple years, Niels Bohr came up with his Bohr model to fix those problems of the planetary model. And his Bohr model had those conditions that you have stationary states, only certain energies allowed, and electrons have to be in one or another. They can't move continuously from one stationary state to another, which means that they simply can't radiate energy as they orbit. So that gave it was basically a condition he laid down that would then say, and that's why it doesn't give off radiation and the electron crash into the center. And they said the angular momentum is conserved. And with the angular momentum conserved and the stationary states and still circular orbits, then you can calculate what the radius is for an orbit depending on its angular momentum and what the energy is for an orbit depending on its angular momentum. That quantum number, n, gave you basically everything about the orbit of an electron. So this was great. It explained exactly the emission spectrum. We had the Balmer series, and of course the Lyman, the Paschen, the bracket, the Funt. It explained all of those perfectly. They were just electrons jumping from one energy state to another and either giving off or absorbing the energy in a photon. But it still had some flaws. Flaws like it couldn't explain the fine structure. When you look at those emission lines real precisely, you see that they split. And the Bohr model couldn't explain the splits. Furthermore, you have some emission lines that are stronger than others, and the Bohr model couldn't explain that. And so that entered the quantum model, and the quantum model is our current model. And we have 4 quantum numbers. Make sure you know what each of the quantum numbers is. Its name, what values it can have, its symbol, what information it gives us. Make sure you understand then how those relate to the orbitals, how they relate to the Pauli exclusion principle and Hund's rule, so you can explain the filling of electrons and how that predicts the periodic table that we have in the back of the classroom. And that is the end of my review. Yeah, sure. Yeah. Yes, the 4 quantum numbers are n, which is the principal quantum number. And it tells us primarily energy. Where E1 is minus 13.6 electron volts, and Z is the number of protons in the nucleus. So that's what the principal quantum number tells us. We have L, which is the orbital quantum number, and it tells us the total angular momentum. Remember h bar, I mean this will be given to you of course, but h bar is equal to h over 2 pi. And then we have the magnetic quantum number, orbital magnetic quantum number, that tells us the orientation of the angular momentum. It tells us the angular momentum parallel to some external applied magnetic field. Doesn't tell us anything until we apply an external magnetic field. Is equal to m sub L times h bar. And finally, we have the spin quantum number that tells us the orientation of the angular momentum of the electron. Yes?
And h bar is equal to Planck's constant.
Divided by 2 pi. Yeah, right there. Built into these equations, we have selection rules. You have n must be greater than L. There was a homework problem that had that wrong. How many people noticed the homework problem had it wrong? A few people. The homework problem, I just sent them an email today, said n is greater than or equal to L. Well, that ain't right. n must be greater than L. If L is 1, n must be 2 or greater. And then we have, just comparing these two relationships right here, the angular momentum in the z direction can't be greater than the total angular momentum. And so that sets limitations that minus L is less than or equal to m sub L is less than or equal to L. L has to be between plus L and minus L. And then electrons only have two possible spin states, so you just have the rule that m sub s is equal to plus or minus 1/2. All right, we're out of time. I'll see you for lab tomorrow when we'll do the test, in case people are confused there.